Okay, so I'll begin by thanking the organizers and everyone concerned for inviting me to, excuse me, inviting me to speak here, and also congratulate everyone on what's been a really great conference this week. So as usual, I have too many exciting things, or at least exciting to me, to tell you that I want to get you excited about, and wasn't able to, as they say, kill enough darlings in terms of slides packed with exciting things to say. So I may not get to the end, but I hope to get to the main points, which are these two. I want to get you to rethink perhaps what you understand about random matrix model approaches to gravity, and encourage you to elevate Wigner to the same level that we tend to that we have for 't Hooft in how we interpret matrix model results, because I think we've been for historical reasons missing out on a big piece of the picture. And so the slogan, if you like, is I'm going to foreground the matrices in the random matrix models, or to put it a little bit more cheekily, I'm going to take the view that a random matrix model is a model of random matrices, and you'll see what I mean in a moment. And actually, I've been saying, and I apologize to many of you who you've heard me sort of banging on about this for over a year now, but I think a number of these things keep needing to be said, and I do think I have allies. I've learned from Julian Sonner. I encourage you to look at his work and the work with his collaborators. In some ways, I think there's a lot of resonances with some of the things going on from the ETH perspective, so I encourage you to look at those works as well. So in view of the time, I'm just going to pretend that I've already spent 15 minutes talking about the usual introductory remarks about JT gravity. So you join me 15 minutes into the seminar where we've done that introduction, and some of our favorite things are on the board. And the key points are, of course, that we have this Euclidean approach we've been doing to JT gravity, and the big, stunning and beautiful result is that the perturbative expansion, that sum over geometries and topologies that we like to do in defining, we think, what quantum gravity should do for us, that's all captured by a random matrix model, and that's the exciting result of Triple S. And there are many variants of this now. There are deformations and other kinds of two-dimensional gravity theories that for which this is true, and that's very exciting. One of the striking things that's still puzzling, of course, when we think about the goals of trying to formulate quantum gravity, is that there's still, in some sense, a puzzle, right? We have this finite entropy, the Bekenstein-Hawking entropy, and we still have this continuous spectrum, which comes out of the matrix model, but it has a different origin, and there's words about ensembles we can talk about, but really it's still not clear why we can't see signs of, explicit signs of a finite dimensional Hilbert space underlying whatever the holographic dual should be. And the key point really is that you're not going to see that unless you go to non-perturbative physics. And so the main thing I've been doing for the last 3 years is formulating things non-perturbatively. And then so much jumps out that isn't apparent at any order in perturbation theory. So that's one of the main messages. So the matrix model approach, I just have one slide. You know the standard words, but it's important just to remind ourselves that this is there, and this is historically how many of us learn matrix models. We have some partition function for the matrix model with some potential. That's not the potential you would use for JT, but it's just start out some quartic potential. And, 't Hooft tells us, oh my goodness, if I expand in the Feynman graphs and order things in terms of the 1 over n expansion, where n is large, I see that I sum over topology. So I sum over all graphs organized by topology and the 1 over n expansion. And then if I tune the model, the double scaling limit is all about then taking large n and also tuning to a critical point where the implicit tessellation of the random surfaces that I'm interested in, that these graphs do, picks out nice, smooth, the universal physics associated with smooth surfaces. And this has a long history, and it's rather beautiful, and I'll get back to some of this at some point. So that's what the matrix model is doing, and the key point is that you can imagine a complicated enough potential to capture fairly complicated gravity theories, including things like JT gravity. And that's implicitly what Triple S did, order by order in perturbation theory. We need to go further than that. So what's the message the main message I want to get across is as follows. Yes, let's try and get these little dots, what's hidden in there. And in some sense, the little dots eat the whole thing and become the big beast in the following sense. So you have a random matrix model, and that is the theory for what that we need to interpret and understand. And the important point to make is that there's a corner of it, which is the place that we usually start with, and the place where we mostly spend most of our time staying in this field, which is the part that we like because it yields smooth random surfaces. Now that's a very sort of 't Hooft'ian thing. I just reminded you what I mean by 't Hooft in this context. But the whole large thing is really more in the spirit of Wigner. And we need to try and understand how to connect the two and how to move out of here and go into the larger story. Now, I should say there's some beautiful work already in Triple S and various other works, and even going back to earlier matrix model eras, where we do, of course, see that there is some venturing out of the random surface corner, various WKB approaches and instantons and what have you, but it's still not really seeing the whole thing. And so that's, I think, crucial to really understanding what's going on. So over the last few years, I've developed tools needed to formulate the full random matrix model of JT gravity type theories, and I'm going to try and tell you a little bit about how that works. In view of the time, I'm not going to get to everything. But the picture that emerges is, I think, highly instructive, and it suggests a somewhat different perspective on what's really going on. So the output of the non-perturbative formulation. So, well, there's a whole bunch of papers developing the tools and understanding that I've written over the years, and including a couple with some collaborators that applied some of these tools then to some special cases. And I should also mention, if you want further examples of the kinds of things that structures are showing up here, there's also been some really nice recent work by my former student Felipe Rousseau and his collaborators at UBC on applying it to even flat space examples. And those are really worth a look at. Very interesting to see a lot of things you can do. Very analogous to what Triple S do for JT, but then you can also do the non-perturbative completion using the techniques that I've been developing. Okay, so this is what I would normally get to at the end of my talks in previous years on this stuff. I'm essentially starting with it, which is that, well, that's the famous Schwarzian leading order disk order in perturbation theory spectrum, the cinch root E that we all know and love. And then you can work hard using the techniques that I'll tell you about to actually complete that to get non-perturbative physics. So way up here, way up at large E, you have cinch root E plus corrections, building you the answer in perturbation theory. But then, if you work hard enough, you can actually see that some non-perturbative wiggles begin to develop. And that's very exciting. And, you know, years ago, that's where we would have stopped. We would have said, we're done. This is it. We've solved it. We've found the wiggles. and that's very nice. But actually, it turns out there's a lot more. There's many more matrix model techniques we have not been using in this field that I encourage you to learn if you're interested in moving further. And that tells you that there's a lot more going on. And in fact, it'll tell you what the origin of those wiggles are very explicitly. And what they are, they're probability peaks. And the way to read this is that you have this first peak is telling you across the ensemble, it's saying what are all the ground states? What's the probability of all the ground states? What's the probability of all the first excited states? Oops. And so on and so forth. Second, third, etc. So in a way, what we're seeing is the first signs of something that we've been looking for, if we're doing quantum gravity, which is that there really is a discrete structure there that the matrix model does know about. Even though it gives us a continuous spectral density, it is a sum of discrete things telling you about that underlying discrete spectrum. So working non-perturbatively with the tools I'm going to tell you about, this is already very exciting progress. We're really explicitly seeing the things we expect to see to tell us there's a finite Hilbert space there. Now, of course, you could go, well, we kind of knew that because the matrix model is a matrix model, but what have you. But it's still doing it explicitly and being able to mine it and get useful information out is paramount. Words only get you so far. So the observations about that spectrum I just showed you, the gaps are set as they should be by the entropy in the usual way. H bar is something that's cheekily called H bar. It'll turn out to be an H bar for something in a moment, but it's the topological counting parameter e to the minus S naught, where S naught is the extremal entropy. And it's exactly where it should be in terms of how it controls the gaps in the spectrum, the gaps between the typical peaks. And moreover, what we see then is that the peaks are broad at low energy. There's a lot of variance in the spectrum. And then as we go to where perturbation theory is, where we do smooth surfaces, we see that they narrow, their variance gets very small, and the distance between them also shrinks. So they form a continuum, and that's where we see smooth space-time geometry emerging. So we're learning something else from the matrix model as well. We're seeing explicitly how space-time geometry can emerge from something that isn't geometrical. And that's, again, I think, another powerful lesson from the matrix model that is extremely explicit. And the other thing we learn is that this is a way that the matrix model tells you how you can discretize the Schwarzian spectrum. Really can be thought of as having some underlying discrete structure. And the matrix model is built from spectra of that type. And it's extremely explicit. So the Wagnerian aspect comes along deep in the matrix model, where there are large gaps possibly in the spectrum, but the Wagnerian picture, where we mix together lots of spectrum, fills in the gaps, and then we come out with a single function that we call the non-perturbative, if you like, matrix model spectrum. But it isn't, in my opinion, it should not be thought of as the JT gravity spectrum, and I'll say that more explicitly in a moment. So, the picture I usually have, and I wasn't going to show this slide in view of time, but I'm going to flash it anyway, is we could have done an alternative history to arrive here. Okay, we can imagine that we were looking. We know about Bekenstein-Hawking. We know we should be looking for some sensible discrete spectrum, some Hilbert space, some finite dimensional Hilbert space. There's some quantum gravity computation for this gravity problem that would yield that spectrum, but it's a hard problem. So and you know, this should sound familiar. We're trying to find this large, complicated Hamiltonian and understand its spectrum. We know it exists, but it's hard. What would Wigner do? Wigner would go, well, I'm going to study the class of Hamiltonians and see if I can characterize it, even if I can't solve for the one explicitly. So try and characterize H statistically, just as Wigner did for atomic nuclei. So you study all H with as many things as you know about it. And the thing we know is that it asymptotes, the spectrum asymptotes to the Schwarzian. So if you study all H's with that leading spectrum, what do you get? And let me glibly say then, this is what he would find, which is, you know, that's what I showed you. So that's the way of thinking about the matrix model. It's it's a statistical thing that comes about because of incomplete knowledge about the problem. There's no reason we should think that the matrix model fundamentally knows the full quantum gravity answer. And of course, Wigner did not conclude that atomic nuclei don't exist or that somehow they can only be understood as an ensemble. And he wouldn't conclude that here either, right? It's a statistical tool that can tell us some really important things, but we shouldn't get too carried away by thinking of it as a fundamental object. Nevertheless, it can teach us lots of things. So what's it for? So it's a beautiful method for doing perturbation theory. It's a beautiful method for understanding a lot of interesting things about the possible duals of JT gravity, or the complete quantum theory of gravity within which JT gravity should be embedded. And it already gives us some wonderful hints about the discrete spectrum, some quite explicit. And very importantly, I think it's teaching us something about being careful about defining gravity to be the Euclidean path integral with the sum over geometries and topologies. I think that's one of the main lessons here. That is not a good definition of quantum gravity, but we already know this because it is CFT. And it's extremely useful for excavating universal features of the possible spectra that can complete to the semi-classical one. And that's what I hope to talk about a little bit more. I'm going to tell you a little nice story about the ground state peak. Just to drive this home, let's talk a little bit about thermodynamics, which is always a good guide for you getting the physics right. If you can't get the thermodynamics right, that's a problem. If we just started with the matrix model spectral density, either to some order in perturbation theory or fully non-perturbatively, and we computed the partition function by Laplace transform, and then we computed the free energy in the usual way, we actually start running into trouble. It starts out fairly well at high temperature, but at some point, the entropy gets to 0 and then starts going negative. And that's a problem, because it should actually go all the way, this is the entropy above extremal, it should go all the way at 0 temperature down to S0, and it's not doing that. So there's a problem, and what is that problem? And the explanation is as follows. What we're really doing is we're computing the average of all of the partition functions in the model. That's what that spectral density is doing. And so if we go ahead and we compute this, we're computing what's called the annealed free energy, trying to get an average which is not as well behaved average at at low temperatures as other averages, and a really nice average, which is better motivated for many reasons, is what's called the quench free energy. You take the average of the log of the partition function, and that's better protected from strange atypical samples. I'll show you more explicitly in a moment. The intuition that we should make this distinction actually first appeared in this context in a lovely paper by Engelhardt, etc. And a number of us tried to begin to compute it in various ways. A lot of the intuition, especially that of Engelhardt, etc., was all about trying to use replica wormholes, smooth surfaces again, to try and understand how to fix the problem. I think it's a very interesting and valiant attempt to do that, but I fundamentally think that the way you really should do it is to do it in this Wagnerian way. So I'll show you how to do it in the next couple of slides. Yes?
The red curve comes from the Jordan approximation.
Actually, even so, it's sort of amusing because it already shows in the Schwarzschild approximation, and so I began to notice this at some point, and I thought, you can fix it, and you start adding some of the corrections, and it still doesn't. It's still not working, and then it turns out that even if you have the full non-perturbative thing, because that's what people were telling me, if you just get the full non-perturbative thing, it'll work, and it doesn't. And it shouldn't. I now understand. I was too confused to publish this, and I just thought, I've made a mistake. And then Engelhardt et al. Began to think about it and explained it very nicely. And then I realized, no, there's no reason that it should work. That was my beginning to realize that we should be more Wigner and less 't Hooft. but I'll show you what happens. So the point is, before we get carried away, let's actually just do a random matrix model, because I think sometimes we say lots of fancy things about matrix models and we forget about the matrices, right? So let's just go back and do what we can do explicitly, which is we can just write a couple of lines of code and just do a Gaussian random matrix. And so there's the usual thing. There's Wigner. We can scale into the edge as though we're looking for gravity. And indeed, we would get, in this case, something that's exactly solvable. That solid blue curve there is, you can write down what that looks like in this case. And those are explicit matrices that I've just binned histograms of to show that it works. The reason it doesn't quite meet is because I'm using 200,000 100 by 100 matrices as opposed to, so there's some corrections. There's a lot of samples, but the matrices are not super big. So, but all the things we need are there. In particular, what you can go ahead and do is bin in the way I just talked about. You can, every time you get one of those matrices you draw randomly, you can order its eigenvalues and bin that way, and then color code. And you'll get the curves that I showed you that I can get for JT gravity as well. So now we can explicitly work out the annealed and quenched free energy and have no confusion about what it means, because we have explicit matrices. And the amazing thing is, this has never been done in the literature as far as I can tell, but random matrices are a wonderful place to actually play with these kinds of quantities. So you can go ahead and do it. For every time I get a sample spectrum, a sample matrix, sample spectrum, I can compute its partition function. So that's unambiguous. It's a number that I get, and then I can either average over that and take the log, or I can take the log and average it over that for all the samples. Okay, and then off we go. And that's what you get. And so the blue thing is this quench free energy. What is it? It's a better measure of what the free energy of a typical member of the spectrum is doing. But there are outliers. There are spectra doing crazy things, and what they do is they mess up the red curve. The annealed free energy is very badly affected by those things at increasingly lower temperatures. And the really great thing about this example is that you can see why that's the case as well. The variance in the peaks grows at low energy. That's telling you have more atypical contributors to the problem. And indeed, that's helping create this deviation. So the quench free energy is saying there's a typical single spectrum that the matrix model is trying to tell you about, that the quench free energy calculation does. So the point is that you can spectroscopically, in a regime, taking into account a regime where smooth surfaces would be doomed to fail because they don't even have any meaning, that allows you to spectroscopically compute the answer. There's the answer for JT gravity, by the way. It smoothly goes down and lands at zero temperature on the average ground state across the whole ensemble. And so I'm going to tell you a little bit more about the ground state itself, or the spectrum of ground states in the last bit of the story. So I think there's an interesting dictionary to be developed here between the Tuftian quantities, for example, the properties of the various wormholes we can have in the theory, and the actual variance you get in the piece, telling you about the properties of the ensemble and the atypical properties of the ensemble, or what have you. I think there's some beautiful. They also connect to two very different areas of mathematics, and so I think there are actually some interesting places where these things can meet. But that's for another time. I have some preliminary results on some of that. Okay, so how does this all work in the remaining 5 minutes? So now let me tell you how to do some of this, because I've just told you about results. Okay, so what really happens is, and again, you can do this all very explicitly in an afternoon. You can learn this all very explicitly for the Gaussian case. What's really nice to do in this class of random matrix models is to construct to construct a family of orthogonal polynomials out of which you can build everything and answer all questions ultimately. And so they're orthogonal with respect to the matrix model measure given by the potential. And there's some recursion relation. So once you have that, you're good to go. You can construct all of them. In the case of the Gaussian case, it's actually just Hermite polynomials. So, it's a very, very familiar sort of animals. So essentially, the recursion coefficient itself that you need to know to tell you how to get the next one is implied by the potential. So if I know the recursion coefficient, I effectively know the whole matrix model. And that's really all there is. I want to construct all the orthogonal polynomials, and then I can answer any question about probabilities to do with the spectra in terms of those animals. When I take the double scaling limit, what happens is that these things assemble themselves in a really nice way. I'm going to skip the orthogonal polynomials that I call P become things I call psi, which are they're called psi. The recursion coefficients become a function I call U, and they end up being, the psi end up being eigenfunctions of some Hamiltonian whose potential is U. So knowing the full matrix model then amounts to knowing what this potential U is. It seeds some Schrödinger Hamiltonian from which then I can get a family of wave functions. Then I compute with the wave functions. For example, the spectral density itself, fully non-perturbatively, requires that you do this, perhaps puzzling, and I can explain where it comes from, but time is short. There's an integral you do over the square of the wave functions over a range for x, and that gives you the spectral density. So this is well known. This goes back several years and was embedded in some of the original papers. But there's a lot more you can do with these wave functions than just compute the non-perturbative spectral density. And I've already shown you some of those results. Let me just say, in the case of the Gaussian, in this case, the function u essentially is just linear in x. And this then defines the Airy problem, and the wave functions are Airy functions. And so when people talk about the Airy model, that's one of the reasons it's called that, because in this limit, the edge becomes Airy. So I'm going to skip a little bit. I have only a couple of minutes left, but I want to at least tell you a couple of things. So basically, you can do this for the full JT gravity. All you need to do, in quotes, is find this potential. And it turns out that it satisfies what in the old language was called a string equation. Oftentimes, what people call string equations these days are just the leading order string equation, but there's a fully non-perturbative ordinary differential equation that you need to find and solve that defines the problem. So those are the sorts of things I've been able to do for various problems, various JT variant gravities. The potential ends up looking like this, for example. Then you have to solve the spectral problem and compute. Now, people often, I hear, sort of when referring to some of the things I do as saying, he's doing some numerical thing and blah, 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 blah. It isn't a numerical thing, right? It really is that in order to show you graphs and things, I have to actually solve these highly nonlinear equations. But the understanding is not just a bunch of numerical stuff. That's really important to understand. There's a very well-defined set of concepts here that are not numerical experiments. Okay, so in view of the time, I'm going to drop telling you the story about mining the ground state in particular, and just sketch out to end how you really understand these peaks, because this is stuff that's well known to the StatMech matrix model community who don't care anything about gravity, and as far as I can tell, completely unknown in our community. And I really want to get you excited about using these techniques. And the point is that there's a lot more we can do with matrix models. So you can build this more general object called the kernel. which is a lovely sort of self-reproducing kernel that about which I can answer any question about the matrix model in principle by phrasing it in terms of this object. And if you ask the right question, you can get some really beautiful answers. And so, in particular, for understanding the peaks and how to get those, you ask about something called gap probabilities. And it was shown actually back in the 60s that, in fact, there's a natural problem. This kernel acts as the kernel of an integral operator that acts on the energy line in the following way. I have a function f, and it'll give me a function g by acting like this on the line. And so you can actually ask questions like, what is the probability that there are no eigenvalues between a and b on the line in the matrix model? And the answer turns out to be the determinant of this operator. It's a Fredholm determinant in the classical sense that you know, classic sense that you know. And so the question then becomes trying to understand this operator and compute it to get that answer. For the Airy problem, this is well known and very famous for a number of reasons. And what actually happens is that you actually, it's rather nice to look at this object. There's the K, constructed from Airy functions, and I just constructed a snapshot for you. If you look along the diagonal, you'll see the bumpy black line going to a square root e. That's the thing that we tend to focus on, the non-perturbed spectral density. But there's all this structure in the off-diagonal stuff, and that's what can give you a lot more information. So what you go ahead and do is compute the following thing, and then I'm going to stop. You can ask, for example, what's the probability of not finding an eigenvalue from minus infinity all the way to some point s? That's a question you can ask. You compute the Fredholm determinant for that problem, and look at this dotted line. That's the result. It's saying if I'm far, far away from where all the eigenvalues, classically I know they're sort of all lumped at 0 and beyond, the probability is almost 1. In fact, if I go all the way to minus infinity, it's 1. And it stays at 1. As I get close, it begins to go, okay, there's some probability that I found one now, and then where the edge begins, it's sort of dropping, and then when I'm far away from the edge, deep in the eigenvalue distribution, it's highly unlikely that I haven't found one yet. So that's how you interpret this. That's a cumulative probability distribution. I take the derivative, and that gives me the probability peak. I can iterate this and do this for, there's a Fredholm determinant for every peak, and I can iterate this and build the sort of things that I've told you about. So since I already know all the wave functions for the JT gravity in question, I can implement this, and so that's how I was able to build all those peaks. And then you can use that to really know what the spectrum or the family of spectra look like quite explicitly, and do all the thermodynamics and so on and so forth that I've been telling you. Okay, so what I didn't have time to tell you, and I'm going to stop here, what I didn't have time to tell you is that, well, first of all, this is a hard problem to do, even in extremely simple cases, do analytically. And so you have to bring numerical methods in to help and things like that. And there's some beautiful methods which I could tell you about. Very famously, some of you have heard about the Tracy-Widom distribution. It's very important. It's the first peak for the Airy problem that has shown up in all kinds of physics. It's some kind of new universality that is present in those kinds of physics that the matrix model captures. So there's something analogous for the gravity case. And so in the recent paper that I haven't talked much about, I was able to find ways of characterizing that even better than just doing the numerics, because it turns out you can actually derive an ODE just for that peak that controls it. And then expanding the ODE in various regions gives you lots of properties of the peak, even though to solve for the whole thing you need to do numerics. So those are the sorts of things that I've been able to do, and I think that's telling us there's new kinds of universality coming from gravity models that tell you about the distribution of things like ground states and so on and so forth. And who knows, those universalities may show up in other kinds of physics as well. So thanks for listening. And I think I'll, rather than throw out my conclusion slide, I'll just stop here and take questions. Yeah.
Hey, I just wanted to maybe try to understand better one remark you just made kind of en passant, which was that you don't think that, for example, certain quantities can be characterized geometrically, and you made a particular comment about the quenched free energy. Can you say a bit more about that?
I think that, okay, there's two steps to the story. The first is that if we definitely start with a single copy of a spectrum, and we're out in perturbation theory, we can see that there's some sense in which it's going to connect to, you know, summing over smooth surfaces and what have you, because the spectrum closes up essentially. It becomes, we might as well just write it as a sum of delta functions and then average, not average, but just ignore the gaps. What the matrix model does is it does that, and it also mixes together lots of spectra, so that we can go deep into regions where there are large gaps, but then other spectra fill things in. So there's no sense in which I'm now, when I'm deep in that region, which is important to get those late parts of the free energy, there's no sense in which I have, you know, any single theory that has random surfaces that pertain to this regime. It's sort of a deeply matrix model region that is best described in terms of spectra. And so it might be that there's some gravitational geometry picture that you could come up with that could do that, but I think that sort of clearly isn't the natural animal in that regime.
Yeah, maybe something like with replica wormholes would do it, because you use the replica trick to get the log of the partition function, and then you evaluate it. You might get still a geometric saddle.
Except that hasn't worked so far, as we know from the lovely work of Netta and collaborators. But there's all kinds of non-perturbative information that those wormholes cannot possibly know about. And you know, we spent 30 years trying to understand how to put words on what the non-perturbative physics beyond smooth spacetimes is for matrix models. And I think the answer is that we should just talk about spectra. And we've just been trying to use words that come from smooth spacetime intuition. And I think we should, why are we doing that? It's just spectra. And then it just becomes extremely clear. I can do the calculations on the back of an envelope. Well, a large N envelope.
A large envelope. Yeah, that's a very nice one. So these plots for the average of log of z, did you do them? You did not explain how to do them, right? Or you did? Maybe I missed that point.
I think I did.
So how? That's not the standard average in matrix models, right? That's more the log of the average, right? The average of the log.
The average of the log is something the matrix model finds hard to do. The matrix model is good at doing the log of the average.
Right, but the average of the log, can we compute analytically at large N using some replicas or something? I thought Brezin had some papers recently, but I don't know the literature.
I'm not aware of any progress in that remark at arbitrary t. There are some really nice things that some, Mirbiani and Janssen were able to do some things at very low t, starting near low t in the matrix model, and being able to do that, inspired by some nice papers by Okuyama. But then that allows you to essentially be near t equals 0 and then expand away slightly.
So the plots that you showed were done numerically. The blue and the red, the blue and the red one. The blue was numerical.
The plots that I showed were then now start again and go. Let me just look at all the spectra that the matrix model is made of, and just enumerate over spectra explicitly because I can make them. Yeah. Having computed the peaks analytically. Yeah.
Thanks for the lovely talk, Clifford. So this Wagnerian perspective of starting with eigenvalues and sort of averaging over ignorance and seeing geometry pop out is very attractive, but it seems somehow counter to our usual expectations from holography that n equals 4 should have some independent bulk definition with metric degrees of freedom or perhaps strings. And it sounds like if you take the pure Wagnerian perspective, you throw out the possibility of a independent bulk definition. So where do you think that stands from your perspective?
Sort of an independent. Okay, good. So you're saying, wouldn't it be nice if I could define, in the spirit of the last talk, at least some large class of the conformal field theories by saying that they're secretly gravity theories, and I have a gravity definition, and you're saying that I can't do that here, and I go, I agree, but that doesn't mean that because the matrix model isn't doing the full job of knowing the whole gravity theory, doesn't mean that there isn't still some work to be done. And it might well be that we find how to embed JT gravity into some UV complete story purely from the gravity perspective, and then turn that around in the spirit of what you're doing and saying that now defines. But I'm saying the matrix model isn't going to do that. That's all I'm saying. But it still can teach us a lot. I just think it isn't the full answer, and it has no reason to be.
Sure.
I mean, I think I hope to have partly addressed that question in my talk, which is that what you can do is you can construct these kind of models or maybe modifications thereof by inputting only some information that, say, low energy observers have access to. But that doesn't negate the existence of the actual full, microscopic UV theory at all. Mm-hmm. And what comes out in the end is a models of this type or generalizations thereof, certainly in high dimensions.
Yeah. Right. The point was it leaves open the question of how or whether you can describe a single dual theory in separate bulk variables, metric variables, or string variables, and how you would do that, and how you would recover the various things that we like and that Clifford talked about in that context.
Sure. I mean, I don't want to, maybe Clifford can say it as well, but I don't think Clifford was advocating that such a thing doesn't exist just because he can construct these models.
Indeed, I'm saying that there's more work to be done, which is exciting, and there are more things to do. We know in principle, right, that we can start with some full string theory background and have intersecting branes and all kinds of things, and end up with some Rising-Norton black hole and take a near horizon limit, and hidden in there is JT in some way, and that's in principle, it's hard, right, and there are many ways of doing that. So it'll give you many different many completions of the leading Schwartzian and so on and so forth, and it completely fits with that intuition. It's just hard, and it's also not clear really how much we learn by doing it example by example. So another thing the matrix model is good for is saying, well, okay, it can be done to get a single copy in principle, but actually let's learn some things about what just staying semi-classical looks like. Let's blur our vision a little bit and get a view of the, pardon my French, landscape of the for those who don't like that word, landscape of the kinds of things that would complete. And I think that's valuable information, and that's why Triple S and everything that's followed is still so central and powerful to how we approach this large problem.
Any other question before we go for coffee break? Okay, so if not, we will resume at 11, and let's thank Cliff again for a very nice talk.